let's get started. And today is kind of important in terms of machine learning. I'll tell you why. So far, we've been studying the traditional machine learning for 6 weeks, right? So I hope you already grasped a basic understanding about traditional machine learning. And what makes today important is we're going to start get into the deep learning. A lot of people are waiting for this moment now, right? So but you will see very soon, deep learning is not something mysterious. You will understand it today. I guess the basic idea is just take 1 minute or two, or something like that. But before that, we should go. Here's the framework for today. And before we get into deep learning, we will review a little bit of the traditional machine learning. You will see the connection between those two types of learning. More or less, they're just the same. And gradient descent, we introduced last week, and today I will give you more details. Excuse me. And neural networks, and deep neural networks, and convolutional neural networks as well. Excuse me for a second. Just gonna drink some water. Let's just continue. And also very popular and special kind convolutional neural networks. I introduced the terms like layers pooling, activation, and some of the examples of deep neural networks there. And as we know so far, we have learned some models of traditional machine learning, like SVM, like the Bayesian classifier, and also the very simple one, KNN, right? And also we have gone through the unsupervised learning, like the clustering. But you probably get the impression like those classifiers are easy to build. The accuracy is quite high. But this is just based on our setting in the tutorial. We're using some, we're doing it on some controlled environment, like for in the tutorial last week, we have the gesture recognition, which has been captured in a controlled environment. And what you have seen there is each of the image contains only the hands, a specific location in the image, right? The illumination are almost the same, and those and the number of images are also limited. And those are some other popular data sets, which was very popular when the traditional machine learning is popular. So those are for facial recognition. You could see they are kindly have that control when those images are captured, meaning that they capture only the face part, and at the same time, there's the orientation of the head has been normalized. There's no tilt and turn around or something like that, right? So this will be much easier for study because we can compare and we have some unified environments to test different classifiers there. And they are there for some reason anyway. And also this is called minus handwriting digits. And those are only for numbers. And those numbers are some kind of normalized as well, because the orientation has been normalized. And even those strokes, even it looks a little bit different from each other, but they're always almost the same style, right? Okay. And this is an effort, even we don't I'm introducing this, not only trying to review the data sets with you. So I just want to introduce some kind of difference, how we look at those samples. Now, here's another example, very popular recognition, palm print recognition. There they have to capture the palm part, they use some kind of points called anchor points to fix the hand to the camera. In that case, only this part of the palm will be captured, and we save a lot of efforts. And the purpose is the same. They're trying to unify those samples. Otherwise, if you take it at a very random orientation or some random illumination, you got to get different types of images there, and will cause a lot of problem. And you could see from here, the images captured by different devices, they look quite different from each other, right? Okay. And however, those are in controlled environment. However, in reality, in real application, this change of illuminations, in orientations, and other stuff are inevitable. Like when you're taking picture of the same object, you probably take from different viewpoints, right? From different distances. And as we have introduced in the lecture one, these are okay for human beings because we are kind of adaptive to such kind of change. We can focus on the specific part we're interested, no matter what kind of distances we're taking that picture or what kind of viewpoint we're taking that picture, right? We're kind of adaptive, but the computers are not, because the images are stored as numbers. A tiny change of the viewpoint distances will cause a significant change of those numbers. So it causes a lot of problem for the computers. And also you see illumination effects, occlusions, background factors, and even for the same class, the cats here, you can see different types of cats, and they're with different colors and different patterns of their fur, and also when you're taking this picture, they are with different poses. Okay, so one example we had last week is I mentioned earlier, the gesture recognition. I know some of students have taken that challenge, and they got a quite high accuracy, right? If you have ever tried that. The reason is, as I mentioned, we look at those images, the orientation are unified, and illumination are unified. So this some kind of ideal for training and testing. Actually, in the example, we haven't extract any of specific features there, right? We're using the pixel, the value of the pixels as the features directly, which gave us an impressive result, quite high, over 90% of accuracy, right? So, however, in the real application, if you have tried it, you will see that like those control, those images captured in controlled environment is impractical in real applications like that, right? Because when your user are using your system, most of the time you can control what kind of illumination they are going to have, and also what kind of camera they have, what kind of gesture or viewpoint they're going to do it. So this is a challenge, actually. We're planning to leave this as one of the assignments for you to try it. Can you use the model trained here to do a gesture recognition there? So that's one assignment. We will give more details. But anyway, taking that chance, I hope you can understand. The data sets captured in a control environment is quite different from those in a real application. There are different reasons. And also, in terms of scale, traditional machine learning works in a limited number of data sets. And also, at that time, the models are quite simple and computational power are quite limited. However, people realized very soon, and this can, the classifier trained with small data sets cannot be used in a larger scale, right? So there's an effort coming out. This example called ImageNet. It's an effort by collecting and organizing the data in a very large scale. So, because as I mentioned, one of the reasons is you don't have such scale of example for training. So they're built it in a very large scale. And here are 3.2 million images in total. And compare back to what we use in the tutorial, it's at least than 100, right? So, it's a quite different scale. And also you could see for each of the class, you could have different types of examples there, like for the vehicle, you got different types of vehicle. Like for the craft, you got different types of craft as well. So, and also in the real world, there's another challenge. Maybe it's not that related today, but we're talking about those data sets, and it will be better to mention it. In the ImageNet, the concepts are organized as a hierarchy, because semantically, you will have the concepts at different levels, like from the vehicle, you have the craft. From the craft, you have different types of craft, and you have a watercraft. And watercraft consists of sailing vessel and other watercrafts as well. So they are organized as a hierarchy. And it's used for some time for recognition. Maybe people use such kind of tricks to build to train their classifier in a hierarchical structures. And you can use that as well. I will explain that later. But anyway, this is very large data sets. And there are many variants of the same class. And it's in a very large scale, giving people the chance that they can train some kind of classifiers which can be used in different environments and also deal with different variants there. So this is ImageNet. And ever since then, people has that opportunity and efforts have been put to train classifiers which can be applied in a real application and in a large scale. So that's one um, other reason which make deep learning very popular, because right now deep learning is considered one of the best solutions to address such kind of large-scale training and things. I'll tell you why today. So let's as I mentioned, we're going to talk about deep learning, and I hope this makes you excited, because I know a lot of students are waiting for it. Okay, but before that, let's review a little bit of the traditional machine learning, and because as I mentioned a lot of times, the concepts are connected, and they're evolved gradually, not something like you suddenly have the deep learning. So, even the terms is fancy. So let's go to a very simple classification question to distinguish from the red apple from green apples. So that's it. Let's see. We have green apples and red apples sold in boxes. I visualize it. You can see them, but let's see. Those are boxes, and you can't see inside. You don't know what's in that box. Is it a green box? Is it a green apple, or it's a red apple or something like that? We're going to use train a classifier, which can tell us what it is, what inside without open the boxes. So this is a task. How can we do it? There are different ways. Let me give some example. Like you can measure the weight of those boxes. And also, maybe usually when you get a product, there are some labels on it which tell you some information, like the date it is made, or the expiration dates, or something may tell you some information about it. Yeah, anyway, you can collect a lot of information from there. Even you probably can open some boxes, right? You open some of them to see what kind of relations between the information you can collect to the actual color of the apples, right? If you can build such kind of correlation, and you can train a classifier, right? So it turns out we can prepare something like a table, as I mentioned so far and used so far. You can collect a lot of information, those boxes, like as I said, the weight and maybe the dates, and maybe there are other stuff there as well. I don't know, but let's see. There are some of them there. They are not telling you it's red apple, green apple, but we hope they are correlated. We just collect as much as possible. And at the same time, we can open some boxes to see what's inside. Then we can put that as a label for the boxes we opened, right? So we have this table. This table will be something like what I mentioned. What's the term? What's the term for it? What kind of data set they are? It is. Now we can use that as, think about the classification framework. We can use it for training, right? Yeah, that's a training data sets. Right? So we can use it as a training data set. Then with that information, we can build a model. And this is quite straightforward. Basically, the same like what we have last week, but I'm going to give you more details. As I mentioned last week, to separate red apples from green apple, you can draw a line in the feature space, right? Because we already have that feature space by collecting information. We can draw a line. And the line can be represented with y equals to a multiplied by x plus b, something like that, right? Even last week we have changed. You can actually unify the x and y like x1 and x2. So you can convert that into matrix multiplication or a vector multiplication. So let's skip that part, and I assume you already know they are just the same. So we stick with those very simple formula for a line there. The problem here is how can we find the best line which can separate those apples, right? So last time when we were introducing SVM, we introduced one way to measure how good it is. That's the margin, right? The margin is the distance of the nearest sample to that boundary. We can use the margin to measure how good it is. But it turns out there are different ways, not only the SVM. So let's put it into more general sense here. And once you can understand how it is constructed in a more general sense, you can build, which will give you the chance to build different types of classifiers there, not only SVM. You can theoretically can build any types of classifiers there. So right now it's quite simple. You have that formula, you have that line. So why don't we, because the way we're doing the classification is we're evaluating this part, if this part equals 0, because you move that y to the right side, and those will leave a 0 there, right? At the left side. Let me just write it. So today I prepared something I can write. So why don't, sorry. Why don't we just use it? All right, so it's a waste. So the thing is, you can move this y to the right side, and it becomes like something like this, right? So, and if it's the line, it's 0, and we can substitute the actual value as a z here, like what we do here. So if z now can be used for as an indicator for classification, if z equals to 0, then you're on that line. I mean, specific example for any of those points, by substitute their actual coordinates into this formula or into this formula, you're going to have the z equals to 0. But for the point like here, if you're going to sample some value x prime, y prime from here, substitute them into this formula, you are going to have the z larger than 0. Otherwise, on the other side, if you're sampling some samples from here, you're going to have the z less than 0, right? So let's put it into more general sense. That's something we already have last week. Anyway, we can for any of the coordinates, for any of the points in this feature space, you can calculate a z there as outputs, and you can do the classification based on the sign of that value, right, as the output. So this is what we had last week. And from here, the thing is, we don't know which line it is. We have to figure it out by select the right A and B, right? Because this is what we have last time. Where is my pen? So A and B, it doesn't work that well. So I don't know why. Okay, so anyway, you have different lines there. Those different lines corresponding to different A and B, right? By given any of the A and B, you have that line defined. So the problem here is find the best A and B, which means the parameters. Let me find it. Why it doesn't work that well? Okay, so now it works. So it doesn't work that well, but it worked. So okay, so the purpose is here, find A and B, which is the best. But at the very beginning, we don't know which is the best. We can randomly draw a line, meaning that we can give a random x prime and b prime, because those a prime and b prime will give you a line. Here the line is 0 equals to a prime multiplied by x, sorry, so x minus y plus b prime. So this is a random line you have, right? So then we're going to keep updating those a prime and b prime and to push that line to the best line we want, right? So so this is the model we have, and this in another way. But the problem is, if we want to make something better, we have to come out a measurement of those better or worse stuff. That means we are going to measure how good it is, the goodness of that line. So this is most straightforward one. We can build something like, because every parameter will give us a z as output, right? We can compare that z to the actual z you should have. We can see the difference between them. Let me go back to here to see what it is. So you have right now, this is a line. The line is z, sorry, 0 equals to a prime plus x minus y plus b. So this is on the line. So any of the point on the line will give you the zero result based on the formulas you have. Here we're actually using the z0 for it. So what we can do here is, because for those samples in the training data sets, we have their features, right? We have the feature extracted at the very beginning in the tables, right? Meaning that we have their features, which means we have the x and y coordinates for them in the feature space, right? So for any of those sample, we can substitute. Let's see, we have x here, x prime here, y prime here. So and it's a red apple. We have the label, right? In that case, we can substitute this into this formula to find out what the z0 will be, right? Because we already have the a prime and b prime selected. So right now, by substituting x prime and y prime into x and y respectively, then we can calculate z0, right? Then right now, for this point, you will have a z0. Let's mark it as 0 prime. Maybe we should write it here. 0 prime, right? So then we can compare this z prime to the expected label, meaning this is the label, red. So what's red we're using? It's 1, right? So because right now the z0 prime should happen again. So this one right now is greater than 0 based on the line we have, right? It's greater than 0. And the red is something, so it should output what? It should output a 1, right? Based on the rules we have. And what the actual label of this sample? It's 1 as well, right? So we can compare between those two values, like we have put. The evaluation is z something compare back to z prime and take that square. So right now they are just the same, which will give you this evaluation as a 0, right? Meaning that the actually match the expected outputs. This is a good example. However, this one is not. So for here, for these samples, you could have the x and y. Let's say x1 and the y1. Its feature or coordinates, and its label is a green. And for green, we put -1 in the data sets, right? So by substitute this x1 and y1 into this formula, we're going to have z 0, 1 as well, which right now is greater than 0, and turns out the output will be -1, right? But oh, sorry. The label will be 1 rather than -1, right? Because it's greater than 0. Based on the rules we have, we should have it like here. If it's greater than 0, we output 1. If it's less than 0, we output -1. So that's the reason we should have it here as a +1. So when we compare back to its label here, we're going to have something like the 1 minus 1, subtract -1, and take that square. Right now the result is 4, right? So you will see here, if it do the classification right, and it will give you a smaller number, right? If it's doing the classification wrong, like for the red apple here, it will give you a 4, which is a larger number, right? So it actually happens the same. This red apple will have the z0 right now as z0 less than 0, and which will output -1 there, but its actual label is 1, right? So when compare back between those two, this is a ground truth, and this is the output guarantee that you have. So which will give you the loss equals 4 as well. So if you make it right, and the loss will be 0. If you make it wrong, and the loss will be 4, right? It's a larger number. So this is quite straightforward. So I take some kind of effort, not that straightforward. I'm not sure if this is clear enough. Is it okay? Or any questions there? Okay, I guess it's okay, right? So quite very simple calculation will make you have some kind of way to evaluate how good a line is. And this is goodness. This is one of the stuff we call the loss function. The loss function. It's quite, now the name loss makes sense, because when I do it right, I have a smaller number as a loss, which means I lost less, right? And if we got a very large number, we lost more. So So that's the loss function, quite straightforward. But this is not the only loss function I picked up because it's quite straightforward here, right? You can define other loss functions like the margins we have in the SVM, right? You can define something like that. Anyway, with this loss function, every time you have a pair of parameters for A and B, and you can evaluate how good it is. Here, you could see actually we summed all the stuff together. We sum them together, meaning that we actually iterate for all the training samples we have. For every sample, we can calculate a loss, right? For every sample, we can calculate a loss, and that's this part. And I means you can consider I as the ID for the sample, right? So for every sample, you calculate a loss and you put a loss together, and you can take the mean of that loss to evaluate how good your parameters are, right? So so this is clear. Then good list can be evaluated. Once we have some kind of number which can tell us how good it is, then we can compare good parameters from bad parameters to make it easier. Then we can update towards the good direction, right, of the parameters. So this course is called learning, trying to learn from bad to good. Then, but how to do it? And this is what we have last week, gradient descents. We can use gradient descents. And here we can review it and at the same time give you more details. You know, the goal is we're trying to minimize the loss function, right? It's a function. And in calculus, we know the minimum output of a function are located at the point where you have the gradients equal to 0, right? But not actually the minimum. It could be the maximum, right? Because to refresh you a little bit, the calculus gives us something like you have a function. Usually, in two-dimensional space, you can represent them as a curve, right? So the gradient is the derivative, actually, located at those points, peaks or valleys, which will give you either the minimal or maximal value for that function, right? So this is what we have in the calculus. So with that knowledge in mind, so it's quite straightforward. If we're looking for the best A and parameters for A and B, we can look for that points which make the loss have the gradients equals to 0, right? So this is the design. Okay, so then it turns out how we can find the points which will give you the 0 gradients. So that's what the gradient descent is doing. So here you could see we can actually gradually update the A prime and B prime we have with their gradients. So this is formula of doing it. And we just subtract their gradients there right now. So the intuition here is, be careful because I'm using a theta. Usually people use the notation, the symbol theta to represent the parameters. So here, the theta can be either A and B. So I just want to make it easier to just pick one theta to represent it. Then with one parameter, we can visualize it in two-dimensional space. and here is the loss function. This line is the loss function, the L. And right now, this two line represents the gradients at a certain point, right? So let's see, right now we have select some of the theta prime at this point, and we can calculate its gradients because we have the loss function defined. Then we can calculate the current gradients. If the gradients less than 0, meaning it's a negative number, and by substitute this one into here, because this part, when this part less than 0, and turns out it's going to be a plus something, right? So, and in case you are at this part where you have gradients greater than 0, again, this could be A and B, A or A, B, or just use 1 to represent 2. Could be something like that. Okay, so when this part is greater than 1, it turns out you will have A prime minus some kind of shifting. So you will see like when it's less than 0, it will push the gradients towards this direction to push the parameter selection towards this direction, meaning that it towards it to the body. And also when it's greater than 1, it will push the selection of that parameter towards the body as well. So because when it's A, when theta is A, it goes the same. When the theta is B, it goes the same. But A prime and B prime, I mean the gradients for A and B are not necessarily located at the same section, right? Because it could be the gradients of A prime right now is less than 0, but a gradient for B prime right now is greater than 0. It happens that way. But if that happens, you are actually doing it in the two-dimensional space, and it could be something like you have 2 dimensions pushed into different directions. They are orthogonal to each other. So it finally will push you to the body as well. Right? It depends on where the body is located. So okay, let me go back to there's one more concept I have to introduce. So this is the idea. However, another thing you have to do is because the gradient could be either very small or pretty large. So it turns out if you use that to update the parameter selection directly, most of the time it's not appropriate because the scale of the parameter and the scale of the gradients are not the same. So in that case, people are using something called a learning rate. Learning rates are trying to control how fast you're pushing the change, right? Because usually the gradients, let's say if the gradients is pretty large, if you don't control it, it will going to be something like that. Without control, if the gradient is very large and next point you're pushing them to here, it could go across the body to the other side, right? And if it's too large, then if you keep doing it, and you are probably have something like this, you're going here, there, here, there, here, there, and you can't actually push them to the body effectively or efficiently, right? That's what we call convergence. you can't convert, the learning can't converge, right? So the idea is you can use a learning rate. Let's see, we can put 0.005. This is one. It just depends on your application. So meaning that every time we can update that selection a little bit rather than that aggressive, right? So it's going to be updated a little bit from here, little bit from here, little bit from here, little bit from here, little bit from here. So you will reach the bottom. And it's the same. If you are putting this weights as a larger volume and the steps are larger, and right? If you put a smaller, tiny volume in every time you update little bit, and which makes the learning slow down. Okay, so that's the idea. It's something you can control that, and people actually has conducted a lot of studies to find out the better learning rates there in between. That's another topic there. I'm not going to elaborate today, just give you a general idea about it. And also extend those to two-dimensional space, you're going to have something like that. And here is your loss function. It's a surface in two-dimensional space, because right now we have two parameters there. In case you have three parameters, you're looking for the maximal or minimal point in a sphere, right? In a ball, in that case. So the ball has density, and you're looking for something like the zero change of densities there. Okay. So these are actually how we're doing the gradient descent, and right now it makes much more sense because we're descending to the valley, right? So it's called gradient descent. So is this clear enough? Okay. Okay. Great. Let's go together. So what happened here, because we're keep changing the parameter, is the process is going to be at the very beginning we have A prime, B prime selected, which defines this line. And after the updating, meaning that we update little bit of A prime, B prime, maybe I should make this minus because we are actually subtracted. And it goes to here, define the second line. And if you update again and again, and finally when it reaches the valley, you have the best line selected. So that's the idea of gradient distance. Okay, let's put stuff together. So you can see here the machine learning is actually a process to find the best sets of parameters here, and which will fit into a model or hypothesis. There we have our lines here. So we have a line as a model. We assume we're going to separate samples with a straight line. So the learning process conducted by updating the parameters with a learning rate towards the optimal loss function, right? The loss function we define. Then the gradients is actually an algorithm for updating the parameters. So these are relations between those terms. And so right now, what the time it is? And check out what the time. Okay, it's 4:27. Maybe we can take a break for 10 minutes. Yeah, come back at for maybe not 10 minutes. We can come back at 4:35. Okay. So then you're ready for neural networks, deep learning stuff.对，很好的一个问题，这个是确定不了。
那也就是说，有可能是这个确定了这样，
对，这里就是说，这里有这个举个最优权最优的问题。如果你有多个的话，有时候如果你的 learning rate 够大的话，你设定很出来一个。对，如果你的 learning rate 比较合适的话，那就可以跨过那些小的包里，到全自由的。通常的话都是靠实验。不过也有一些办法嘛，比如说你有一种方法叫 grid search， 你先在你的参数空间里面把它划分搞，然后你在那个参数空间里选一些每个格子里选一个点出来，试一下。这样子的话，你就会大概的对这所空间有一个了解，和它的整体的运行。这个很难的，你要在你的 laptop 上本来就是一件很难的事情。通常大家都是跑一个子集，分析可能通常只关注一个。ImageNet 虽然我稍微这儿介绍，但是因为它比较早，第一个比较大，值得介绍一下。所以它有保证相关的后面会介绍。他们比较那个你们那个方有来确定性，那个话那个是所以你有咗 A prime 同 A prime 先你先就變呢個算呢個方面其他可以做係啊，佢全部都有。所以咧，你跟住咧，呢個 value 就會俾你一個 output。頭先講之前，你有咗呢個 value 之後，佢就會話俾你個 output。所以即係話一個 output 其實都話俾你個 label 嚟嘅。如果係 one 嘅，佢就係所以咧。呢個 var 呢個 output 就可以你就攞咗呢個 value 先。你有咗呢個之後咧，你就可以係已經係啊，你而家係 one 係啊，係啊，計出嚟係啊，即係所以咧， 嗰個 label
呢一個真係計出嚟嘅數字係咪等於？
係啊，
係咪快過正方先？
可能係啊，
就發到呢個收嚟，但係因為可能有 A
係啊，
即係譬如呢個係副手，
係啊，
即係唔會叫做一計出嚟咯，所以佢就唔係等於
係啊，
代表佢係 A 啦。所以呢一個
係啊，
即係 expect taxing cases 真係計出嚟嘅時候，究竟係一模一樣。
係啊，係㗎，
所以就可以即係做前面嘅質量可以收到，即係可能一啲就係錯，咁樣睇翻佢。
係啊，如果佢俾到你一，佢頭先嗰個係 minus，
即係計錯，
佢計錯咗，俾同樣嗰個 loss 都係負，
所以就可以揾到佢嘅。
係啊，呢度就係全部加埋一齊，平分咗。呢個咧就係話呢啲你錢自己喺度最加到個位，因為咧嗰個 loss function 你而家未係嗰個 loss，佢個 function 嚟，所以你所有嘅 function，如果你想揾你最加個數，就係最大或者係最細個位置，其實就係佢嗰啲gradients 係等於 zero 嗰啲位。呢個係
最接近。
係啊，其實嗰個 gradients 直接佢 derivatives，你其實之前個 calculus 應該有學到，其實咧就係每個 point， 佢其實都有話俾你知嗰個 change fast。快或者係慢。如果咧呢個 curve 而家佢個 slope 係好大，佢個 change 就係好大。如果佢比較平嗰陣咧，佢個 change 就好慢。所以所以話咧，你個 curve 而家就係咁啊，係啊，其實咧佢就可以拉一條 line， 為 estimate 嗰個 point 嗰啲change 係咩嚟嘅，所以咧嗰個 slope 嗰啲嗰個叫咩？anyway 每個 point 都有咁樣嘅 slope， 嗰個 slope 就係呢樣嘢，佢 derivative。係啊。係啊，
即係個 change，所以我哋而家希望做 change 最穩定。
係最穩定到位。係啊。係啊。
所以呢一個分析，
呢個咧就係話俾你知點可以揾到呢個，因為你可唔可以直接揾到佢嘅，因為嗰個 loss function 呢啲parameter 仲未定。所以話咧，你試下咯，試多次。即係話咧，你有咗 A prime B 咧，你而家嚟高，就好似你而家揾咗你揾咗呢個位之後咧，你就可以記下而家嗰個 slope 嗰個 gradient 係點嘅。如果佢係如果係個 false 嚟嘅，你記埋呢個之後，其實都加上呢啲 small value， 所以加嗰個效果咧，就係 push 到佢 select 呢啲 value， 因為加就往呢邊走，加就往呢邊走。佢如果係加係啊，如果佢揀咗佢往呢邊走，
即係佢最尾個 objective
係啊，揾到呢度個 value。
因為佢都係
係啊，
即係將呢個方向擺去最低。
係就係咁咯。
咁多 train，
係啊，
因為 training 又係影響到個 model。
係啊，
所以而家我哋希望點樣提升啊？
係啊，
其實喺數學上
係，
即係呢啲就係一個所抄，即係 train 出嚟就同出入嘅呢個係啦 medical 即係最平嘅。 抽象的，
最后个来一次。Okay, let's just continue. Actually, I got a good question from students, saying like how do we know there is only one valid or optimal points there? It turns out we don't know most of the time, because we don't know what the eternal distribution of this loss is going to be. So it turns us into something like if we are putting up smaller learning rates, meaning that every time you change a little bit of the parameter selection, which will help you to converge to somewhere we call local optimal. And if you don't want it to converge to local optimal, you want something global optimal, you probably need some strategy will encourage your learner to take a bigger step to then you can go across that local value there. So there are different strategies there to help you to take a balance between the global optimal and local optimal, but I think that's beyond the topic today. We can introduce something later. But anyway, that's a good question. You can think about it. Will help you to grab a better understanding about this. Okay, starting from now, we're going to actually introduce the neural networks. As I mentioned, you already got everything of it. I guess you prepared my previous lecture about traditional machine learning. As I mentioned, you can actually grab idea about the deep learning or neural networks within 1 minute. So it's quite simple because we're going to draw a line to divide the apples there, which is we have formula for line there as well. It's just a calculation, right? So we can take them into a graph. We can use this graph to represent that calculation, meaning we could have 3 nodes which represent. So right now we have 3 nodes. Let me switch to the, sorry. And let me switch to the pen. So right now here you have 3 nodes. 3 nodes, we can use them to accept the input. And because the calculation of that formula is every time we selected A and B, for any given samples, their coordinates about X and Y here, you can calculate following that formula to get a Z, right? So here we can do something like, for this example, because we have a coordinates, we input them to X and Y here. And for another example, we can do the same to input them here to here. And then we multiply each of this value with the age connected. Here is the age connected X to Z. So you're going to have something like A multiply X. And here is a minus weight here. So you're going to have a minus Y. So here, 1 is fixed, the value. It doesn't take any of the inputs. So this 1 multiplied by B is going to be itself. So you have 3 values here. Let me put them down here. A multiplied by X and minus y, and together with the b. And this is what actually you're looking for. By putting those, by sum those values together, you're going to have the z. And with the z calculated, and it can be put into this node. So it's just a representation of calculation, right? But it's still the same of what we had previously. Okay, so here, this is a neural network, actually. They already have the neural networks. It's just about the representation. It's just the same. Here, we actually call those as neurons. Sorry. Those are neurons. And between neurons, you have some edges, connections there. And we follow that rule like every time we multiply the value on the neuron, on the node, with the edge connected, the weights on the edge. We gave a value for, give a value for the, on the nodes, and we calculate by multiplying the weights on edges. Then we send that result to the next nodes connected. Okay? So this is the way we're doing the calculation. And this is neural networks already, even it's quite simple. Is this clear enough? Yeah, because it's just the same of what we have previously. Then, well, it turns out we can do the rest stuff the same. But we can give a label based on the value of z to check if it's greater than 0 or not. So this is the same. This is a set-list neural networks. However, why? What makes neural networks that popular? It just stays. It's just the same like what we have. Definitely not. Check out this one. So here we have more nodes there in the graph, meaning that the calculation has been changed. It turns out we're going to have a result on D rather than what we have on Z, right? We have more edges and more nodes there. What is the correspondence of this one to the model we have, meaning the lines? Anyone want to try? What this is actually calculating.
In different ways. You try to multiply in different ways to get different.
That's right. That's right. We are going to get different
We
ways.
try different combination of weights.
Oh, yeah, that's right. That's right. So that's almost perfect answer. But let me give you more information. Instead of using one line to separate them, we can actually use more lines, right? So here we can actually use 3 lines. It's like we're using 3 lines here. You can see the correspondence here is like, here we are using x, y. When we're doing this, by sending the value x, y to z1, here will corresponding to 1 line, right? So when we're doing this, by sending those 2 values to z2, we are defining another line. And the same, where we have the 3rd line here. So then what we have is we're taking the sum of the results from 3 lines, right? So meaning like we have 3 lines and we summarize the result together. Sometimes this will be more reliable by just rely on 1 line, right? So, and sometimes it will converge faster than just use 1 line, because when you're using 3 lines, actually you have something like 3 probes in the feature space. to figure out what the best. Then you collect information from different probes to make better selection at the end. Right? So this is correspondence. And at the same time, you will see like this actually defines a different function. Previously, that's a linear function here, right? With two parameters as input. But here we have more internal variables here in a space. So this is more complex function than what we have previously. So you will see here by stacking more nodes, or sometimes we call those layers. This is input layer, this is hidden layer, this is output layer. I will give you the names later. Anyway, there are different layers there, right? You can actually extend the number of nodes vertically, or you can extend the number of layers horizontally there. So anyway, every time you have done the extension, you're going to have a more complex function. So here you probably will end up something like a curve rather than a straight line, right? In some of the cases, like if we're going to have a lot of red apples here, and some of the nonlinear function will be a better selection to separate the apples. Okay? It just depends on how many features we have, what kind of features we have, and the distribution of those features and samples as well. So, okay, but I hope from here you really seen and you're really seeing like the advantage of using neural networks is we haven't seen the advantage. We haven't talked about the advantage. We just mentioned that there is a correspondence between this traditional model and the neural networks, right? So what's the advantage exactly? I didn't say it straight. I didn't say it, but I hope you might really figure it out.
Since you calculate 3 lines at once, you take the best one and you go from the best one with 3 new values.
Yeah.
You take the best one every time. Instead of having the best of 1 and the best of 3 every time, you calculate more at once.
Yeah. Okay. This is a result, actually. You tell some aspect of it by using the examples I gave. Meaning that what we're saying is we're having a better model than what we have previously, right? We're having a better model, but this is a result of using neural networks. And you want to try?
Minimum and loss functions.
Minimal and loss function is something. It's actually the same as what we have. That's a part I'm going to introduce. Okay, let me tell you. The advantage here is you define some simple calculation, right? Just put the values on the nodes and multiply the weights and send to the next layer, right? This is a very simple rule. And you are building a more complex function by just adding the layers, following the same rules of calculation, right? So this meaning that I think the advantage of neural networks is using a very simple rule for calculation, but gave people the strength of building more complex function. And at the same time, actually, without knowing what the function is, exactly is. That's the advantage of neural networks. That's what makes it very popular. Because previously, if you want to do some research on machine learning, you got to get a very good understanding of mathematics. You got to know different optimization methods, and you got to know different types of function, approximation, a lot of theories there. But those have somehow gone when you have a neural networks, because everybody can do this by adding layers and adding nodes. And the computer is going to figure out what's the best parameters and function for you. And that's the part I'm going to show you. By adding layers and nodes, it's very easy because every nodes and weights are following the same way of calculation, right? The rest you can just let the computer do it. You don't have to programming to do it by yourself. In traditional machine learning, you have to program by yourself. Oh, this denote X, the other denotes Y, and A and X and Y has to be used at different types of calculation, right? And in terms you have Z, you have other variables, you have to define the calculation all by yourself. But by using neural networks, you don't have to do that, because just follow that rules for calculation, right? You just define the structure, computer do the rest. And but this is just the structure. What we're talking about here is just a calculation. We call feed forward, because we're feeding the data into the nodes. And this value, after calculated, they are forwarded to the next layer, right? So it's feed and forward, feed and forward, feed and forward. And this is neural networks. And however, there's another part we introduced a lot that haven't been connected to here. That is, how can we do the training? Right? Previously, we update the function by select different parameters using gradient descents. That's the training part. That's the learning part. And here, you are going to have the same questions left to be answered. That is, how can you select the weights on edges, right? Because for nodes is easy. Nodes, you have some initial value from the samples you have, and meaning that those nodes will get the value from there directly. But for the weights, it's remain the same. You need a weight, define weights, right? Like in the traditional machine learning, we have to find the parameters. And then here the weights on the edges actually the parameters, right? So go back to here. So those are the weights. Okay, those are the weights. A and B are the weights, right? So how can we find that weights? And since we already have the gradient descents introduced, it can be used here as well. So, and that's the part I'm going to introduce. Once you have more layers and more nodes here, how can you use the gradient descents to find the best weights for all of them? If you're going to do something in the traditional machine learning, you have to define that. You have to figure out what the function is exactly, so you can find the gradients for every variable or parameters there. So, so let's see, when you are putting the nodes and edges into the neural network structure, and we can use the we can evaluate the outputs like what we have in the traditional machine learning by building a loss function, right? Because no matter what kind of structure you have, what you cares about is if it outputs the number you're expecting, right? So once you know what's the expected number, you can compare that number to this output to there. And you can build a loss function like what we have. So in a very simple structure there, we're calculating the z, the line there, right? We're compare back to the expected z there to build the function. And we can use the same, actually. We can do the same. But let's go back to here. So let me just clear. So, okay. So here you can, let's see, for every, let's see, this is sample one, you have a Z1. You can compare it to Z. Let's see, what's the sample we're using? Maybe we can use the Z1 prime. Maybe it's not decent, but doing that way because it's actually maybe confused a little bit with A prime stuff, but let's just use it. It's suddenly coming to mind. Let's Z1 prime is an expected label for this, and it's 1 as well, right? So let's see Z for apple 1. Let's see, it's an apple 1. Let's put that's number 1. Okay. For number 1, you're going to have a value here, like Z1. You can compare it back to the expected ground truth here. Then, because this is a loss function. Then you have the loss for the point 1. And for the same number 2, you do the same stuff. You have a loss 2. And you put all the losses together to estimate the overall loss there, right? So then you can use the back propagation. You can calculate the gradients to the parameters here, like what we had previously. It's going to be, you are calculating gradients of L on A prime here, right? So here you already have this function. It's easy to calculate what the what it is, right? So what you're going to have, let me do it for you. So the loss function is L equal to 0 to Z prime, all right, Z prime there. And take the square, it's going to be Z square minus 2 Z and Z prime and Z prime square, right? So this is L. Right now, it's nothing to do with A. Sorry. Let me just calculate the gradients over Z first. What's the gradient of Z? According to your knowledge of calculus, it's 2Z minus 2, right? Is that right? Yeah. So anyway, it doesn't matter. If you don't remember how to calculate the derivative, the gradients, it's okay. So anyway, you have 2Z minus 2 as the gradients over Z. So if you're going to update the Z, you're going to use the gradients, but we're not updating the value on nodes. We're interested in those weights on age, right? So we're looking for something, the gradients here, meaning that we're interested in this one. However, right now we don't have the correlation between the A and L, but it's actually we have. What we have is a representation of Z using A as parameter. So in that case, we could, from here, we could calculate the gradients of Z over A, right? So, right? Oh, what's that? Oh, it's easy, right? It's just X. It's just X, right? And you can do the same for B. It's just 1. Okay, so let's recall something like if you are going to calculate some kind of gradients and derivative of functions of function, right now it's something like L is a function of z, and z is a function of a, right? So remember, there is a chain rule. The chain rule in the calculus, which will tell you, because right now what you're doing is actually, because L is a function of z, and if you're going to find the derivative of this, you can use the chain rule. Chain rule will tell you if you can get it by calculating the gradients of z or derivative of z, and at the same time you multiply the gradients of z over the a, right? So this is what we have in the gradients. Then look at it. Right now we actually already have everything we have. Even forgive me, it's writing as a mess. So this part we have here, right? This part we have here already, right? So in that case, we find the gradients on A already. Then we can use the same updating strategy we introduced previously to update the weights, right? And we can do the same, very same way like B. But in this specific example, actually fix two weights. One is here. I don't want to update it, and I fix this value as well. That's a part design, and this is what you can do with neural networks as well. You can fix some of the weights and fix some of the values here to build different, to give you different types of flexibility by control the model, to control the model, right? Okay, this is quite simple because this is something like a 1 layer or 2 layer neural network, quite simple. But when you're stacking more, what happened here is you can actually propagate the gradients using the chain rule. So right now for D, like what we have done previously, once you have a loss function, you should be able to find out the gradients of D regarding the function loss function L, right? So you're going to have this, and for every weight, let's say if it's ABC, you're going to have the chain rule to find out their gradients, like right now in this specific example, it's D over A, right? So you're going to find it here using this chain rule, and you can do the same with B and C. Then after that has been calculated, you will see you already have the gradient at A. Then A is related to Z1 and D as well. So you can calculate the gradients here as well, and you can update them back using exactly the same way for every weight you have. It's like you are calculating the gradients from the end of that neural networks and backwards to the input, right? So it's like every time you calculate the loss at for each of the nodes at certain layers, and you use that as a loss, and also according to the chain rule, you updating the weights back towards the input. So, and that's the reason it's called back propagation, because you're propagating the gradients towards the inputs in a reverse way, reverse direction with those feed forward. Right? Feed forward is from input to the output, the gradients is output to the input. Right? So this is clear enough. Okay, good. I guess because we have introduced a lot of gradient descents, this is easy to understand. So the advantage here, again, you can see the back propagation, it just will do itself automatically. The neural networks will do that. You don't have to do it. It's just based on very simple chain rule, right? It can be calculated automatically. You don't have to write the code by yourself. You just have to write very simple rule of calculation. So that's the advantage of neural networks. And deep neural networks with the neural networks in mind, deep neural networks is just something like or more complex neural networks which have more layers and more nodes there. Oh, it's nothing new there compared back to their, conceptually, right? So why? It takes effort for people, take decades for people to figure out deep neural networks. Actually, is one of the best solutions. The reason is, at the time, neural networks, what we have right now is the third time neural networks getting popular. There is already the first time, second time, and right now it is the third time. The reason is previously people have limited computational resources. They cannot build such deep neural networks. They can't do the calculation. So it's impossible for them to build more complicated neural networks, which will, at the same time, as I mentioned, once you have more layer and nodes, the function became more complex, right? So, meaning that it will give you the capacity of classification using a more complex curve, right? Rather than very simple straight line. Okay, this is deep neural networks, and with deep neural networks, the back propagation will just follow the same chain rule. You got a lot of judges there, help you back propagate the gradients, update the weights as well. Okay, now, well, I think we're ready for a few more concepts or tricks there. So, first of all, we have introduced what the neural networks is, but why it's called neural networks. So this is quite intuitive, right? Because this is actually a neuron, an actual neuron in our brain. So there are soma, that's the core of that neuron. It works like it will receive information from other neurons through those something called dendrites. And those information passed into here to here and processed. Then it will send out called a link called axon. Axon will send that information to different other neurons through that terminals. So you see, it's quite similar to what we have, right? We have the value here and we send it out through some of the weights of the edges here. And we connect the neurons together like the actual neuron in our brain is connected. So then actually it is connected as a graph, a networks. So that's the reason it's called neural networks. Quite straightforward. Okay, let's go further. Other concepts is there are different layers, different types of layers, like we have introduced. There are input layers for taking the inputs. There are output layers to get the output results. And there are some layers in between. We call them hidden layers. That's the part people are, most of the time, they don't care about. And at the same time, because so far we are actually connecting the nodes between layers all together. We call them fully connected. layers, but it turns out we can put them partially connected. Why we have to do it? This is actually very popular way of putting them partially connected. What's that? Okay, it's not something new actually. It's what we have. That's one of the reasons where we have introduced the filters. The filters is something you apply a templates or a filter on the images, and then you slide this way all over that image to either remove the noises or detect the edges. Right? That's what we have, the filters. And the filter, you see, filter is a very powerful tools to build a lot of things. And at the same time, I'll actually introduce, you can actually change the weights on filters for different purposes, right? Like you can extract LPP from there. And also you can define different way of using those weights for different purposes as well. So this can actually use in neural networks. So you can see here, here's a filter. And the convolution is something you apply that filter on that image. Think about, you can think of an image, every pixel of an image as a single neuron. You can connect it, every pixel to one neuron, right? Because every pixel have a value and it can be used as an input for the input layers, right? Then, in between that different layer, let's see, this is input layer, this is a resulting layer next to the input layer, and you can apply those filters. So what's the process of the convolution using filters linked to the idea of that neural networks calculation? That is the weights on the filters serves like the weights on the link on edges, right? The linking edges. So it's something like you link this to one single neuron in the next layer. I mean, this line neurons to one of the neuron in the next layer, right? So those are edges already built. And you can use the weights of the filter. You put those weights on the filter on the links here, okay? Because according to our definition, in every feed-forward step, you are multiplying this value to the weights on the edge, corresponding weights on the edge, and you put them there. And you sum all those results together as a result for this one, right? This is what we have in the filters. And it's the same. It's the same like in the neural networks, right? So what makes it different is first, these nine neurons are only connected to here, right? At least this one only connected to here, and those are connected to there as well because we're actually moving the filters over the image, right? But anyway, they are not connected to all the neurons in the next layer. They're partially connected. Okay? And that partial process is the same like the convolutions using filter we have traditionally, right? So it's like we're doing something like the edge detection using the filters, right? So by doing this, it's like we can pre-process the image. For example, if the edges are useful, if we can use that filter to pre-process the inputs to find out the edges first, then the rest of part of neural networks will automatically build some kind of classifiers based on those edges. You don't have to extract some edge-related feature by yourself, right? So this part clear? It's quite actually explained the connection between the convolution and those neural networks. And also, it makes a lot of sense, right? Because you can pre-process that image. And the most fancy part is in the traditional filtering using convolution, we define the filter weights by ourselves, right? But here, through the back propagation, the neural networks will figure it out by itself. What's the best ages detection or the other filtering weights fit best for your problem of classification? You can figure it out by yourself, by itself. So that's the fancy part of the neural networks. Okay. Okay, putting those together, there's one more concept because it's partially connected. We call it local receptive felt, meaning like this part of the results is this result is from a local part of the previous layer rather than of them, and this one affects connected to this one. It's a receptive felt of that neuron. And different neurons have different part of felts there, right? Or you can take it in reverse way. This part contributes to a certain neuron there. Well, okay. So it's the same, like we are summarizing a local feature to the next layer, right? Okay. So another thing is I've already introduced the weights can be updated by backpropagation, and meaning that neural networks figure it out by themselves. And actually, you can instead of using that weights by training or filtering by training, we use some kind of fixed filtering. You can consider this as a fixed filtering. What we're doing is for a certain range of the layer, we summarize the value in this region using the maximum. We pick the max to there, or we can pick the mean there as well. And even you can pick the minimum there as well. So like those 4 blocks have one output here in the next layer. But sometimes you can use either the max operation or the mean operation. This is like a fixed filtering strategy, which can summarize the result, and also it's reduce the size of that inputs. The other one concept is called activation, because in the real neuron, when a neuron receives the information at the soma, it actually will not doing something like what introduced previously, just sum them together to send it to next. You can do that as well. But actually, in the real neuron, it will slightly process that information and send them out. So meaning that we have the same in the neural networks. We call them activation function, meaning for a node receive the information from previous layer, they will sum it, but at the same time, it will do some kind of filtering as well. You can consider it as a filtering, and also you can consider them as a normalization or something else. For example, this is one activation function. This one is actually mapping the value into either 1 or 0. This is a mapping by taking the sign of that value. And the sigmoid doing very similar but a little bit different way. They're mapping the values into the range of 0 and 1. So it's kind of normalized that value, right? Otherwise, like we introduced previously, if you got very large variance of that distribution, the scale will cause problem for your calculation. Sometimes either the number is too large or too small, your computer can't do it accurately. Or sometimes if you're doing calculation between two numbers with a very large difference between their scalability, and you cause a lot of problem by either multiplying them together or add them together, because the dominating one extremely large number but dominating the results, right? So this makes it more fair by converting the numbers into the same range. So in the future, when you're either adding them together or multiplying them together, that with a very similar scale, and the calculation will be more fair. And also the reduce function completely ignored those negative numbers and putting them all to 0. And for the positive numbers, it's just leave it as the same. So this is another popular activation functions as well. Activation is a step you taken before you actually sending out the result to the next layer. It's called activation. And also, and this is basically what all the concepts you need to know about neural networks. And for the convolutional networks, for the network using the convolution, the filters, we call it convolutional neural networks. Quite straightforward, because it's using the convolution, right? So that's also, in short, we call it CNN. CNN is actually what makes the deep learning popular. So it's a quite important work. Let's see what CNN, a general structure of CNN is. You have some kind of inputs there. Usually we take the image directly as the input. As I mentioned, you can connect every pixel to one neuron and input layer. Then it goes to convolution and activation as well. And the convolution is like using the filters, like I mentioned. And it will be filtered, activated, filtered, activated, filtered, activated. And you can use the pooling in between. And then at the end, you have some kind of result as a certain layer. We can consider the result of that layer as a feature. That's the reason it's usually called feature maps. And feature maps is sometimes a matrix according to our calculation, right? It's actually a tensor, because a lot tensor is a set matrix there putting together. But actually you can flatten them by putting those values on those tensor matrices as a one-dimensional filter. That's called flatten. Like you're extracting all the values from a matrix and put them into a one-dimensional array or something when you're doing the program. Right? So you can put them together anyway, flatten them as a one-dimensional feature vector, and it will be considered as a single layer as a feature vector. Then you can connect them, use a fully connected layer like what we have introduced in previous slides. Then it will automatically do the calculation and finally you have the results calculated. And here, what makes it different is in previous sample, we have a single output there in the last layer, but here we have 3 of them. Usually people are doing a classification like this because one value, maybe it's good for a binary classification, meaning that you have 2 classes to classify. But most of the time, you have multiple classes there. So you're going. What they're doing is, for example, you have 3 classes: the horses, zebra, and dog. You could have 3 nodes representing the outputs of the probability of the input sample belongs to a certain group. Like, so the first node is for horse. It's actually gave you a probability of the input sample is a horse, counting a horse. The image of horse, actually. So you can do a similar thing. Then you can compare those ways to come out the final result of decision, what it is. Simplest way, just pick up the max value, max probability to make decision. Okay. Okay, that's the convolutional neural networks. Is this clear enough? I guess it's just quite straightforward with the concepts we have introduced in previous slides, right? All together as a framework. And okay, so good. Then we can apply that general structure to some famous neural networks. Here is one. It's called AlexNet. AlexNet is kind of the first CNN which attracts tremendous attention, because the story is people build ImageNet, then they have a very large data set, enable people to train classifier in large scale. Then people have tried some traditional classifiers there. They got some improvement and they are also excited about it. But it seems like they reach a bottleneck of the performance. But suddenly in the year, something like, if I remember correctly, it's 2012 or something, if I remember correctly. So here comes AlexNet. AlexNet outperformed all of those traditional classifiers by using those neural networks called CNN. So, so it attracts a lot of attention here. That's the reason. And also, I think that's the first neural networks where it makes deep learning really popular, like today. So you'll see, AlexNet has an image there. Actually, it's well resize the input into a small patch, 32 by 32, because they don't have that kind of computational facility to take larger images here. So they have to resize it, shrink it actually to smaller sizes. Then it go convolution and go convolution. Then they finally use the fully connected layers at the end. Then it outputs something at the end. So this is a general structure which matches what we introduced previously, right? And it's quite simple from a perspective of nowadays. And this is another one, is VGG, built by Oxford, and that's another one brings significant improvement of performance. So the reason is they stack a lot more layers there as well. But this follows what we have previously. They have inputs and convolution layer by layer. 5 basic set of convolution, then reached here. Then they build 3 fully connected layer here at the end and output there. So you will see here to follow the general structure, but they're using different combination of convolution and pooling and activation as well. So, okay, here comes the last one I'm going to introduce, and it's another thing makes makes a significant performance improvement, which is called ResNet. The problem ResNet is addressing is we know that by stacking more layers, we're going to have more complex function defined, right? However, at the same time, people figured it out when the number of layers reach some kind of degree, you can't have performance change. Even the performance will drop there. People observe that. You could see here, at the very beginning, they are using very shallow networks, and the NX line with 8 layers, and it outperformed. This is actually the arrow. So the smaller, the better. So so those are significant improvements by using NXNet. And then the next year, they got better performance by fine-tuning it. But then it goes to 14. And VGG, like what we have introduced previously, have much more layers, 19 then they got better performance. Then the GoogleNet are with very similar layers there, so they got very close performance as well. But they are very conservative at that time by stacking number of layers. So it's something around 20 at that time. By putting more layers, layers more than 20, you probably get a performance drop there. So what's the reason? What's the reason why that happened? But here you could see ResNet stacked 152 layers and got another significant improvement there. And it actually outperformed those previous model significantly, like shown here. But why? How it's happened? And that's why it's important not because of performance, but at the same time, there are some kind of tricks of ResNet introduced, which make it possible for people to stack in more layers. The trick is quite straightforward. It's here, shown as here. So the reason you got the performance drop is once you got more layers, because every time we're using something introduced like the chain rule to update the weights, right? So when you have more layers, the chain rule will help you to stack more and more gradients for calculation, and you can go further and further, right? So when you have more layers and the chain becomes much longer, and every of those gradients are actually in the range of -1 to 1, meaning like the absolute value is less than 1 most of the time, right? Meaning like during the calculation following the chain rule, the actual gradients are shrink, right? And it's going to extremely small numbers there. Even theoretically, it makes sense, but by calculation, when you got very small numbers approaching 0, you're going to have something called rounding errors. And other errors as well, because it's actually extremely small, right? Like you're going extremely large, you got a synchronization of overflow, right? So, and that's the reason you can't get performance improvement by stacking more layers. But a very simple technique used in ResNet avoid some kind of just that problem. So what they have done is here you can consider this part are traditional stacking of layers in the CNN. However, they have done something like this is from last layer, result from last layer. Then they copy what you have from last layer and add them to the output of this layer. It's kind of strange. Right? You're copying the input to the output. Yeah, this is what they have done. And this is a very simple technique, but it brings significant improvement. The rationale is actually I've already put it here. You could see here's the final output HX. Here is the current outputs. The X is input from last layer. And Fx, let's consider Fx. Fx is a function defined by current layers, because every layer is a function, right? every layer takes input from previous layer and process it and give outputs. That's a function. The result of that function is the output of the current layer. We call it fx here. We denote it as fx here. So here by adding, usually this, if you consider this shortcut, we call it shortcut sometimes, and this x is ignored. The fx and fx, the hx and fx are the same. However, by adding this part, you will see in the chain rule, when we're calculating the gradient of L over X, you're going to have, according to the chain rule, it's going to be this, right? Because Hx right now equals to Fx plus X, so it's here. Then you're going to have what you're calculating, when you're calculating the gradients, you're going to have this number plus 1 here, because x, the gradients of x over x is 1, right? So this will make, like, during the calculation, you have a number always greater than 1, right? When it's greater than 1, it's not shrinking. It's some kind of always keep in almost the same range around 1. So meaning that when you're stacking more layers, no matter how many layers you have put theoretically, the numbers stay with a certain range here. It will be better for calculation. Okay. And so, but this small change by adding the shortcut change the rationale at the same time, making it like every time we're not actually learning a mapping of input to outputs. We are learning some kind of relation, like the difference between the input and outputs. In related to the label of the outputs, the actual outputs. So this is maybe take some efforts here. So what we have learned here by fx, if we don't have the shortcut, it's just a mapping of x to some of the outputs, right? By adding the x, we are learning something like the outputs, the difference between the outputs in related to an expected by, right? Here we are learning to the expected directly. So see the difference? So here fx is learning the difference because we are adding this to here. So that part, that fx, this internal part, is learning something called residue. That's the reason it gets the name resname. The RES means residue. So, okay, I might be a little bit confused, but it doesn't matter if you don't get it. But I hope you get it, the gradient part. How does it address the gradient descent chain? Vanish, people call it gradient vanishing problem, because your string can finally it vanish. Okay, that's a resonance. The last neural network works I'm going to introduce today. That's all. And I hope you enjoy. Any questions?
Are we required to like implement a REST or X like from scratch?
Say it again.
Do we need to like write the code of REST or X from scratch, like in our example?
You mean you're learning for your learning, right? You mean, do you have to start from scratch, from S line? net to other neural networks. It's not necessary, completely. It's not necessary. And so my suggestion is when you start building an application, you just check out we call SOTA, the state of the art, SOTA, state of the art. And people are checking this. What is the SOTA methods for different applications? So far, we're introducing classification there. And usually you go to their directory, and most of the application, we just have to apply it. And that's easier and more efficient to start. Use the SOTA model and see what the SOTA performance is. And after you run the SOTA model, you got some kind of outputs from there, and you're going to analyze outputs. Especially, you have to check out the examples you failed to give the correct prediction. And usually you will figure out some reasons. Most of the time, my experience is it's just about the variance of the illumination or something similar, as I introduced the viewpoint stuff there as well. Meaning like if you can do some simple normalization, it can improve the results. That's what I mentioned. The early image precision stuff is really useful. But nowadays, a lot of people don't hear about it. They don't even know there is something called pre-precision. They hope the neural networks will figure it out all by itself. So, anyway, like another example is probably it will be useful. In some of the application, the part they are interested, we call it ROI, the region of interests. Like when you're doing the facial recognition, you're interested in the face part rather than the background. That part haven't been taken care of well. Like they are used a very small face with a very large background all the time, which will push the neural networks learning the patterns of the background rather than the face. So you can use some kind of technology by taking that faces out for training. That will improve the result. So this is a very simple example. Anyway, you get the SOTA and run it, analyze the results, and figure out a way to fit the model better, to figure out a way to fit in the value in a better way, which usually will improve the results directly. If you're interested in research, you guys probably it's okay. You start with Alex Knight because it's quite simple. You can check out the code. There are many implementations there on the internet, and I think it's a either starting point. So it's based on the purpose you're doing it. Okay, other questions? Okay, thank you very much. We finally reached the point of teaching deep learning. So we're going to introduce more from this week. Thank you very much. Okay, see you next week. Okay, bye-bye.